Hello everyone, my name is Sahar Badihi from the University of British Columbia in Vancouver, Canada, and I'm here today to present our work, ARDiff, a scaling program equivalence checking via iterative abstraction and refinement of common code. This is a joint work with Faridah Akinotcho from UBC, Professor Ely from NTU, and my advisor, Professor Julia Rubin from UBC. And now, please meet Alice. In the video, we say how to check whether two humans are identical twins. And here we see two versions of similar code. The developer made a change in line 6, returning B instead of B multiplied by A. We modeled that example after a real change in a third-party computation-intensive library. Looking at the code, it's hard to say whether these two versions have the same functionality, but they actually have, because the change statement is executed only when y is equal to 0. In this case, the value of b is also 0, so the method returns 0 in both cases. More formally, the question that we answered here corresponds to the equivalence checking problem. We say that two versions of code are functionally equivalent if and only if, given the same input, they produce the same output. One of the most popular and useful techniques to establish equivalence checking is by using symbolic execution. So in the rest of this talk, I first briefly tell you about symbolic execution-based equivalence checking techniques and outline their limitations, which prevent them from proving or disproving equivalence in many practical cases. I will then describe our approach that overcomes these limitations and will show how it compares to existing techniques on a set of benchmark applications inspired by real applications from the numerical computation domain. To get us started, let me briefly remind you what symbolic execution is. It's a static program analysis technique that runs the program with symbolic rather than concrete values to explore all possible execution passes of the program. Running program with these symbolic values, here alpha, beta, gamma as an example, produces a symbolic execution tree. Each pass in this tree represents a pass in the program, which includes all statements executed given a particular input. A pass can be summarized as conjunction of its pass condition, which is a formula describing the conditions satisfied by all branching statements along that path, and its return value, which is also calculated in terms of the input symbolic values. Method summary is the disjunction of all pass summaries because each pass can be taken independently. Equivalence checking with symbolic execution then translates into using a solver such as SMT to establish whether two summaries are equivalent or not. But in practice, SMT solvers cannot deal with large complex expressions such as those with nonlinear arithmetic or loops, and that leads to many unknown results. One approach for reducing the number of unknown results is called differential symbolic execution, which we refer to as DSE. DSE aims to simplify the symbolic summaries by abstracting blocks of code common between two versions, which skips executing them symbolically. In this approach, common blocks are represented by uninterpreted functions. And the rationale is that the uninterpreted function abstracts internal code representation and guarantees that, given the same input, it produces the same output. In order to do the abstraction, DSC collects all variables that are defined in the block and represents each individual variable with its own uninterpreted function, which accepts as input all variables used in the block. DSC relies on idea that code is big and changes are small, and not all details are necessary to prove equivalence. So it can hide complex code that is not needed to prove equivalence. But in this case, after introducing uninterpreted functions, we also lost important information by hiding that when y is equal to 0, b is also 0. Thus, DSC cannot prove equivalence in this example. Like in the twins cartoon, hiding too much information is not useful. Impacted summaries is another approach for simplifying symbolic summaries. Instead of abstracting common code blocks, it identifies statements impacted by the change, which we highlighted in red in this example, and only considers those in the summaries. That is, it prunes unimpacted parts of the summaries highlighted in green, and formally proves that only considering impacted parts is sufficient to prove or disprove equivalence. Even though impacted summary reduces the size of the summaries, it can leave in the summary complex statements that are impacted but not necessary for proving the equivalence. This left complexity will lead to unknowns returned by the SMT solver. For example, the function line 2 is impacted and contains nonlinear arithmetic the current solvers cannot deal with. But this line is not even necessary for establishing the equivalence of these two methods. So just as we saw in the cartoon at the beginning of this talk, hiding too much information from SMT solvers, as in the case of DSC, is not useful. On the other hand, exposing too much information to SMT solvers, as impacted summaries does, is also dangerous. And that's where our insight comes in. We aim to find an optimal abstraction which hides complex statements not necessary for establishing equivalence, while keeping the statements that are needed to prove equivalence. We developed this idea in an iterative abstraction and refinement approach called ARDiff, which first abstracts all common code as DSC does, and then refines over approximations produced by such an abstraction using a set of sophisticated heuristics. Here is a high-level overview of ARDiff. As the first step, Rdif abstracts all syntactically equivalent statements between two versions of the code using uninterpreted functions. Next, it produces symbolic summaries for the abstracted methods, and then asks the SMT solver to prove equivalence of two generated summaries. If the solver can prove equivalence for the abstracted code, the soundness of the abstraction guarantees that the concrete version are also equivalent. In this case, Rdif outputs equivalent and the process terminates. Otherwise, the result is not equivalent or unknown. But that can happen because abstracting too much information prevents the SMT solver from reasoning about the code in full, as we just saw in a running example. Thus, Rdif checks if the summaries still contain uninterpreted functions and whether refining these functions can help produce an accurate result. If not, the current result is simply returned to the user. Otherwise, we need to select an uninterpreted function presented in the summaries to refine. The selected statement will be skipped from abstraction in the next iteration, and the process will repeat again until we prove or disprove equivalence or there is no uninterpreted function left in the summaries. One of the core contributions of our work is how we select the statement to be skipped in the next iteration. Or saying this differently, which uninterpreted function needs to be refined. We devised a set of heuristics to identify such functions efficiently. Our heuristics works on two levels, summary level and code level. For summary level heuristics, we look for uninterpreted functions that have the highest chance to be useful when proving equivalence. First, we check if there is an uninterpreted function whose value can make the summaries equivalent regardless of the values of other functions. The rationale behind this heuristic is that if such value exists, and the function indeed can have such a value, no other functions need to be refined. Second, we check if there is an uninterpreted function used differently by the compared summaries. Such functions are better candidates for refinement because they were more likely to lead to non-equivalent summaries. Functions selected by these two heuristics, or all functions, if nothing was flagged by these heuristics, are passed to the next stage, code-level heuristics. Here, we aim to pick one primary candidate with the simplest code, avoiding complex constructs such as nonlinear arithmetic and loops. The rationale behind these heuristics is that, everything else being equal, we want to start refining from the simplest statements that are unlikely to introduce additional complexity for SMT solvers. Back to our example, even though both red and green lines were abstracted in the first iteration, applying heuristics 2 and 3 result in refining the statement in green line while keeping the statement in red line abstracted. Thus, we can establish the equivalence by just hiding and exposing enough information. For our research questions, we first evaluated the impact of each proposed heuristic on the performance of Rdif, and then we evaluated the effectiveness of Rdif against existing solutions, DSC and impacted summary. In this presentation, I will focus on the second research question only. For our evaluation, we started with the benchmarks from existing equivalence checking techniques, which includes 16 equivalent and 12 non-equivalent pair of methods. These benchmarks are relatively small and contain no complex statements. We extended these benchmarks with another set of 57 equivalent and 57 non-equivalent cases, starting from another set of benchmarks collected for testing the ability of SMT solvers to deal with numerical computations. As these benchmarks didn't contain before and after the change versions, we systematically injected changes drawing the number and the location of the change randomly for each benchmark. After selecting the number and location for injecting the changes, we picked the type of the changes based on the class of the version that we want to produce, equivalent or non-equivalent. To produce equivalent cases, we used existing code refactoring techniques to split loops and extract variables, and also inserted dead code, such as redundant assignments or unreachable code guarded by conditions that cannot hold in practice. We inserted these changes to the randomly selected locations. For non-equivalent cases, each change can be an insertion, a deletion, or an update of either arithmetic operation or conditional statement. For example, One change can be update of an if condition by negating the condition. And again, we inserted these changes to the randomly selected locations. The results of our evaluation show that Rdif outperforms both DSC and impacted summaries in terms of correctly solved cases for both equivalent and non-equivalent classes. The improvements are more major for equivalent cases, as proving non-equivalence is generally more difficult to any equivalence checking technique. Specifically, comparing Rdif with DSC, Rdif benefits from refining just necessary information required for establishing equivalence, while DSC abstracts all common code, ignoring its impact on checking the equivalence. Rdif solves 28 more equivalent and 10 more non-equivalent cases compared with DSC, where the average number of iterations helped Rdif to arrive at these correct results for equivalent cases is 1.6, and for non-equivalent is 3.3. The higher number of iterations needed for non-equivalent cases is because proving the equivalence of abstracted methods is easier than disproving it. That is because Rdif conservatively continues to refine uninterpreted functions when intermediate results show non-equivalence, to ensure that the result is real and not an artifact of the abstraction. While impacted summaries does great in hiding complexity of unimpacted code, it over-approximates the statements that are required to disprove equivalence. Comparing Rdif with impacted summaries, all equivalent cases solved by impacted summaries are solved by Rdif as well. In addition, there are 12 cases solved by Rdif but promptly flagged as unknown by impacted summaries, and that was mainly because impacted summaries deemed a complex statement impacted and included it in the summary, even though the statement was unnecessary for proving equivalence. For non-equivalent cases, there are 5 cases where Rdif could produce the correct proof when impacted summaries resulted in unknowns. But there are 3 non-equivalent cases solved by impacted summaries which result in unknowns for Rdif. In all 3 cases, impacted summaries was more successful because the changes impacted only a very small portion of each method. As a result, impacted summaries could prune many unimpacted clauses in the summaries and output non-equivalent. Rdif, on the other hand, does not include logic for calculating the set of impacted statements. It thus kept refining uninterpreted functions, even if not necessary, until it ran out of time. Extending Rdif with additional heuristics to consider which uninterpreted functions contain impacted statements could help avoid such cases in the future. To summarize, in this talk, we focus on the problem of proving equivalence of 2 versions of a program. Specifically, we focused on method-level functional equivalence established via symbolic execution-based approaches. We discussed existing symbolic execution-based equivalence checking techniques and their limitations, and then presented Rdif, our iterative abstraction refinement technique that mitigates these limitations and allows scaling the equivalence checking. We also contributed a benchmark of realistic equivalent and non-equivalent cases and demonstrated the effectiveness of Rdif by comparing it to the state-of-the-art approaches on this and the other existing benchmarks. We showed that Rdif outperforms existing techniques in terms of the number of equivalent and non-equivalent cases it can solve. The implementation of Rdif and our experimental data is available online. Thank you for your attention, and please feel free to contact us with any questions and follow-up thoughts.